Hi, in this video we're going to be talking about section 10.4, polar areas. Specifically, this will be part 1, where we'll deal with simple areas, or at least simpler. And I want to recall from Calc 1, or Calc AB, if we had a picture where some function was floating up in space, we had y equals f of x, and we wanted to estimate some area here, what we ended up using were rectangles. Maybe different height rectangles, maybe circumscribed, maybe inscribed, it didn't matter. Eventually, we started with the area formula, rectangles like y times x, or f of x times x, depending on what x was, depending on what y was, or depending on what f of x was. And we asked ourselves, well, gee, what if we wanted to make this more accurate? We would start looking at small changes in area. That's what the D stands for. And those would be found with using the same heights with small changes in x. And if we integrated both sides, that's where we came up with our formula, that the area underneath that curve should be the integral of the y times f of dx, or f of x, right? The integrals of f of x were a good way of getting the area underneath the curve. All based on the simple idea of rectangles, rectangular coordinates. So that's why we were using rectangles. So in polar, we're dealing with circular motion or coordinates. So the idea is we have some function now, and it's maybe a wavy guy, like that. And we want to use pie type shapes. Slices of pie, slices of pizza, however you want to picture it. So we would be starting with the area of a sector. A circular sector is what we would call that pie shape, which was 1/2 r squared theta, where theta was the angle there and r was the radius of the sector. Okay, so you may not have seen this circular sector formula before. You may have seen the one from degrees. So in degrees, you would have had the theta portion, the angle, over 360 times pi r squared. But if you convert 360 to 2 pi radians, that's how we would get back to this area of a sector formula. And if you've never seen either of these formulas before, it doesn't really matter. I'm just trying to show you the same story we had from the Calculus 1. So the differential of this area, the derivative of the area, you could think, a small change in the area would be found by using 1/2 the same r squared, but a really tiny change in theta. And therefore, what we're going to get here is the area would be 1/2 integral of r squared d theta. And a lot of books, a lot of authors will put that 1/2 inside. It really doesn't matter. As you should know from calculus, we can put constants in and out of the integral. It has no effect. One thing I'd like to make sure we talk about clearly, here the bounds were like letters A and B because they represented x values to x equals b. Here, again, we'd be talking about theta values. Alpha and theta equals beta. All right? So, we're going to have a lot of integral formulas that'll come up. Because you're going to always square r, we need to make sure you guys remember or learn for the first time, if you're coming from AP Calculus, special formulas like the integral of sine squared theta d theta and the integral of cosine squared theta d theta. For all the calculus we do in AP Calculus, this is not one of the topics you need to know for the AP test, so it often gets excluded. It's totally fine. It's totally okay. We don't have to worry too much about it. It's not going to be that bad. We're going to use the double angle formulas here. So use double angle formula. Formulas, plural. What that means is for sine squared theta, we're going to convert that to 1/2 1 minus cosine 2 theta. And I'm really not asking much, just that you trust me that this is the formula. Okay, that's what we would do. For cosine, we have positives. And for sine, we have negative. But they both end up being 2 theta there. And just so you have a flavor of how this goes, or to warm up, I'm going to ask you to integrate that. So please pause the video and try to integrate that on your own. 3, 2, 1. I'd probably distribute the 1/2. And this should make it integrable. This should have been easier to integrate. Integrating 1/2 with the theta is 1/2 theta. For this cosine guy, we're going to have 1/2, that constant. The cosine is going to want to become sine. The integral of cosine is sine. Keep the inside the same. And then the derivative of the inside was 2, so we'd have an additional 1/2 plus c. Okay, so that's how these formulas will end up looking. And then you would plug in your bounds or whatever. But this is the formula for working with even powers of sine or cosine. I want to be clear here, in general, if I had sine squared u, we would get 1/2 1 minus cosine 2u. Now, why am I saying that? Because a lot of students freak out if it said something like 4 theta to begin with. They say, well, I don't have a formula for 4 theta. Well, theta was just a placeholder, so I'm just getting 1/2 1 minus cosine 2 times 4 theta. Okay, it's just replacing the u. The u would be 4 theta, so I'm going to replace the u with 4 theta. Which again is 1/2 minus 1/2 cosine 8 theta. So it just still doubles the inside. It's not that complicated. Don't freak out. You'll be fine. All right, so let's do some examples of this. Find the area of r equals 1 plus cosine theta from 0 to theta to pi. Sorry. So quick, what's this shape? What would this look like if I graphed it? You should know if you've mastered the stuff from 10.3. This is a Limacon. It's centered on the x-axis, and it's actually a very nice Limacon. It's a cardioid. I almost said cordioid. So something like that. We don't have a nice formula for this. We didn't learn one in geometry. We just want to use our formula like they taught us. So what we would have here Sorry, like they taught us, is I mean, like I'm trying to teach you right now, like what's in the book. So what we have here is 1/2 r squared d theta. I'm going to integrate this from 0 to pi. That's the formula for the area they're asking us for. I'm going to be really clear about what area that's giving us. This area should start at theta equals 0, go through theta equals pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and at pi, we're back to 0. So what shape did I get? Notice how it radiates out, again, like a lighthouse or like radar. This area is the top half of the limacon, of the cardioid. I'm not asking you to memorize this, I'm just saying that's what it is. And I want, if you understood what happened in 10-3, I want to make sure you understand why that's the top half of it. Okay, so we have area would be, I'm going to factor out the 1/2. And you should be able to try this problem out on your own. It foils nicely. And this kind of thing right here, you're going to get all the time because we're going to always be squaring. So that cosine squared of theta needs to be changed out using the formulas we just had. So one more time, I'm going to go back. You could just rewind the video. Please write these down. Please try to memorize them. It'd be helpful. And we're going to use the cosine squared one. Right? So I'm going to just keep the 1/2 on the outside. 0 to pi. 1 plus 2 cosine theta plus 1/2. 1/2, not 1/2 again. 1 plus cosine 2 theta. So that pause is me looking at the formula, because every year when I start teaching this class, I have to start remembering those formulas too. And that's where we are in my life. I'm starting the year out, September. So 0 to pi. I'm going to combine like terms. It's going to be 3/2. 2 cosine theta is not a like term with cosine 2 theta. And again, that's why I gave you the little warm-up on the other side. Please take a second, try to actually do this integral, this antiderivative. So I'm changing color because something important's happening here. 3/2 theta to sine theta. And then what we just talked about, it'd be 1/4 sine 2 theta due to the chain rule. And that's from theta equals 0 to pi. And we're just going to finish up evaluating it. 3/2 pi plus 0 for sine plus 0 again minus 1/2 0 plus 0 plus 0. Sine really doesn't like pi, really doesn't like 0. So overall, the area of that top half is 3/4 pi. That's it. You're gonna be like, oh yeah, that's it, just a page worth of integrals. It's really not that bad once you get used to it. The whole limacon, how would you do that? You shouldn't have to necessarily go from 0 to 2 pi, although that will work out nicely. If you went from 0 to 2 pi, would it work? Yes. But you could also use symmetry, and that's going to be a running theme today. Just double what we had. Squeezing it in there for no good reason. Okay? We're going to do an explicit example like that, but I'm just going to try to be really clear right now. A lot of these problems will have a nice symmetry, and it would be making you a lot faster if instead of worrying about the bounds, this is my big hint, instead of worrying about all those bounds, that you just found half of it or a nice convenient portion and then multiplied. So let's talk about one more example. Let's talk about find the area enclosed by one petal of r equals cosine 2 theta. Really quick, one petal, they're telling you it's going to be a rose. So one thing I'd recommend you do is try to graph this to get a sense of the bounds and what's going on here. So we're going to start at theta equals 0. We'd have 1. And then we're going to get back towards 0 in that petal shape. When is the first 0 of it? Can you tell me? The first 0 is when we're at theta equals pi over 4. Okay? Because normally cosine, right? Cosine 2 theta equals 0. We're talking about 2 theta equals pi over 2, 3 pi over 2, stuff like that. And we divide both sides by 2. So that ends up being half. So 0 to pi over 4 is 1/2 of the petal. And this is what I mean when I say we're going to use symmetry. If we're talking about 0 to pi over 4 is 1/2 of the petal, we should use symmetry to talk about the whole petal. All right? If you want to see a full picture of it, you would get a nice rotation in the next quadrant. Okay, when you do that petal, that would be from pi over 4 to, I think, 3 pi over 4. I think I did that math right. And you can do stuff like that. If you're good at graphing, you should be able to come up with lots of different bounds that would work out. I often think it's fastest, though, and that's why I'm going to show this method of finding half the region and doubling it. So what do I mean here? So if I took the area from 0 to pi over 4 of my rose, which is cosine 2 theta squared, 1/2 r squared d theta. It's an annoying formula, but you'll get used to it. What I have here is 1/2, okay, is 1/2 petal. One more time, it'd be 0, pi over 6, and then pi over 4. There's really not much life to this petal. It just dies off at pi over 4. And that would be the formula for half of it. That's half of the petal. So what do? We multiply it by 2. So what's in the red brackets is half of the petal. What's being multiplied by 2, here I'll change it to black. Once I multiply by 2, I'm getting the whole petal. I hope that argument makes sense. Please, please, please make sure it makes sense. We found the area of half the petal, and then we doubled it. The 1/2 doesn't mean it has... This 1/2 does not mean it's half of the petal. That 1/2 is coming from the formula. This 2 is coming from, that formula from 0 to 2 to pi over 4 is only half the petal, so we need to double it. Okay? To be clear, there's lots of stuff going on. Please, please, please be careful when you're setting these up. So we're just going to do cosine squared to theta. And here's the situation I told you would happen. We need to substitute, and now the inside's something other than just plain theta. So try to write it out. We should have 1 plus cosine 4 theta. Beautiful. And now you might be saying, but Mr. Levin, where'd this 1/2 come from? This 1/2 came from the formula for trading out cosine squared. Again, this is really messy. Just be careful and you'll do fine. I'm going to distribute the 1/2. That's just my style. 1/2 plus 1/2 cosine 4 theta d theta. Integrating, getting 1/2 theta plus, it'll be 1/8 sine 4 theta from theta equals 0 to pi over 4. Should be 1/2, let's just pi over 8 plus 0 minus 0 plus 0. So pi over 8 is the full petal. What if they asked you all 4 petals? You should remember that this has 4 petals. If they asked you all 4 petals, then you'd have to quadruple this, which is times 4 from the beginning, or times 8 for that 1/2 petal. Again, there's lots of ways to do this problem. Just focus on what you're doing. Be very careful, and you'll do fine. Good luck on the homework.